So today, last day of lecture for the semester, we're going to finish covering a little bit about antiderivatives today. In terms of things that you have left to do, you have a skills quiz 10, which will be due tomorrow. The answer key for that will go up tomorrow. You have a homework set, which I believe is due tonight, if I'm not mistaken. So you'll finish that up tonight, and we have an exam on Monday. All the material for the exam is up, including the practice exam. Do we have any questions right before we get started here this morning? All right, well, if there are no questions, let's look at this first example together. This first example is designed to kind of answer the question, why do we need antiderivatives and what do antiderivatives help us with? So imagine that we want to find a curve whose slope at each point is given by the function 3x squared, meaning we know what the derivative is because the derivative tells us the slope at every point. So we know what the derivative of our function is, and we want to find the specific function that passes through the point 1, -1. So based on what we talked about in Wednesday's class, I claim that you can do this. The procedure for doing this is take an antiderivative of the slope value, which is 3x squared. So take an antiderivative of this and use this extra point to figure out the value of the anti-differentiation constant or integration constant c. So I'm going to give you a second to try this. I want to see kind of where we are. But this is one of the major things that antiderivatives will do for us, is allow us to pinpoint specific functions that meet certain criteria. Let's go ahead and give it a try. All right, you've got about another 30 seconds to enter an answer. All right, well, it looks like everybody that's logged in entered one, so we're good. The correct answer here is C. So x cubed minus 2 is the correct curve to find. I want to talk about this in a little bit of depth here, and the reason I want to talk about it is this is sort of a problem that's indicative of the direction that calculus is going to head in for your classes that are coming up, Cal 2, Cal 3, and then eventually ODE, which is ordinary differential equations. So this example that I just gave you is an example of solving a differential equation. Here's what you were given. In this problem, you were told that the derivative of y with respect to x was equal to 3x squared, because you were told the slope at every point was 3x squared. You were also given a point of information. You were told that y at 1, so when x is 1, y is -1. So when x is 1, y is -1. These two pieces of information together, a equation that relates a curve with the curved slope and a point together form what we call an initial value problem, also referred to as an IVP. That's a part of what we call a differential equation. So why do we care about antiderivatives? Well, the primary reason we care about antiderivatives is because they're going to allow us to solve differential equations. And it turns out that differential equations are the language of mathematics that's most suitable to modeling a variety of things. And so you're going to learn a little bit more about this in Cal 2, and all of that is meant to prepare you for the differential equations course. That is what my area is differential equations. And so if y'all go on to take the ODE or PDE courses, the two differential equations courses, you're going to see a lot of antiderivatives in those courses. So this is what we were trying to solve in this problem. And the way we handle it is just with a simple antiderivative here. So if you take this equation, dy dx equals 3x squared, if I take the antiderivative of both sides, so I'm going to take the antiderivative of the left side with respect to x and the antiderivative of the right side with respect to x, then what you notice on the left-hand side is you get a cancellation to occur here where the dx term cancels. So you've got the antiderivative of dy is the antiderivative of 3x squared dx. Now, it's been a while since we talked about differentials. We only spent a brief part of one class talking about them. We're going to talk about them a lot more in Cal 2. But this dy that's here, I don't know if y'all remember the definition of that or not, but the definition of dy is y prime of x dx. That's the definition of the differential. So really what you're looking at over here is the antiderivative of y prime dx is equal to 3x squared dx. Now, if you look, that's the exact same thing as what we started with here, right? dy dx is the same thing as y prime. So this was a little bit of a circular argument here, but I wanted to just show you the notation and talk about what happens to convince you of the fact that anytime you take the antiderivative of the differential, all you get back is y. So the antiderivative of dy is just y, because the antiderivative of the derivative, those cancel each other out. So what you'll end up getting here on the left-hand side is the function y of x. And what you get on the right-hand side is the antiderivative of 3x squared, which is just 3x cubed divided by 3 plus a constant, or x cubed plus a constant. So we know that the y values in this problem are according to the function x cubed plus c. And if I want to figure out what the value of c should be, then I'm going to enlist the help of this extra point that I'm given, because I can't solve this problem without that extra bit of information. So if I use the fact that when x is 1, so when x is 1, y is negative 1, then I have negative 1 is equal to 1 plus c, or if I subtract the 1 over, negative 2 is c. So all of this tells me that in fact, the curve I need is x cubed minus 2. So this is why we really ultimately care about antiderivatives so much, is they allow us to solve small differential equations like this, which are very, very useful in a lot of modeling. We're going to look at 2 modeling problems today that deal with antiderivatives, and our approach is going to be very similar to this on those problems. One thing I did want to show you is, we've struggled with a lot of students that take Cal 1 and then go on to Cal 2 struggle with the whole concept of the antiderivative plus c thing. Like, why is it plus c? Well, this is a great example to illustrate why it's important and why the antiderivative is not unique. On this problem, I asked you to find a curve that passes through the point 1, negative 1, whose slope is 3x squared. So if I had just asked you to find a curve whose slope at every point was 3x squared, then all I'm telling you is to find the shape of a curve that has that profile. And so if you are just being asked to find a curve that has the same shape as having derivative 3x squared everywhere, then all of these curves here, x cubed plus c, those all have the identical same shape. So all of these curves, as I'm manipulating the c value, all of these curves have the exact same derivative. So to recover a specific curve, I have to specify a point that the curve is supposed to pass through. And we said that c equal to -2 is what we found. And c equal to -2 is the only curve of this shape that passes through the point 1, -1. You can see it right here. So the only curve of this shape that passes through that point. All the other curves of that shape will not pass through that point, but that's the only one that does. So that's what we were finding. You said you did the end a little bit differently. You plugged it into point slope form. Well, your curve isn't a line, so I don't understand why you would use point slope form. Maybe I'm misunderstanding what you're saying. All right. So let's try another one that's related to this, but it's slightly different. So on the previous problem, we started with the first derivative. You were told that the first derivative was 3x squared. And then from that, you were supposed to find the curve that has slope 3x squared. Here, we're going to start with the second derivative. So if I want to find the curve that has second derivative given by this function, then I need to give you 2 points. I need to give you a point for the first derivative and a point for the original function, because you're going to have to go backwards twice. So this is an example where you have to go backwards twice. I want to see how you handle it. Given that you've seen us go backwards once, I think you can handle going backwards twice, but I want you to try it first, and then we'll talk about it. So here you're just going to enter the actual equation that, or the actual polynomial that you come up with here. So find the original function if it has a second derivative given by what I have there, and it passes through the point 0, 1, and at the point 0, it has slope -3. So just give me the polynomial. You don't have to write y equals or anything like that. Just the polynomial that satisfies this problem. All right, you got about a minute left. I think there is an integral in Desmos. Let me look real quick. But I don't think it's not going to actually calculate the antiderivative for you. Yeah. So CJ, if you go to the keyboard down here at the bottom on Desmos and go to functions, it will graph the antiderivative of the curve. So for example, the first function that we looked at today was x cubed plus c. So if I just asked it to do x squared, I think it is only going to let me do definite integrals, which is something we'll talk about in Calc 2. Yeah, it's only going to do definite integrals for you, it looks like. It doesn't look like it'll graph. And you can't put times either. So yeah, it'll only do definite integrals. This is something that we'll talk about in Cal 2. So nothing to worry about for this course. And you're welcome to use, those of you that are going to go on to take Cal 2, you're welcome to use Desmos for your calculator in that course as well. All right. So I think a lot of you have answered. Let's take a look at the responses. Multiple correct answers here. Over half of us got it right. The correct answer is down here at the bottom, but I want to take a look at it with you and talk us through a little bit of this. So, our goal on this problem is to find the original function or recover a function whose second derivative is given by this polynomial and whose first derivative and function have specific points called initial conditions that we're going to use to solve for the constants of integration. So in particular, we're just going to basically take antiderivatives. That's the name of the game right now in this section. We're going to take antiderivatives to tell us what's going on. So if you take the original problem, which is f double prime equals this polynomial, what I'm going to do is take an antiderivative with respect to x of both sides. Now, once I've taken that antiderivative with respect to x, on the left-hand side, the antiderivative of f double prime will be f prime. Because the antiderivative undoes one of the derivatives. I know what you're thinking. Is it possible to undo both at the same time? Yes, kind of. We'll talk about something like this in Cal 3, where you've got two antiderivative operations acting on a single function. This is called a double integral, but we're not quite there yet. So if I take the antiderivative of f double prime, I get f prime plus a constant over here. I'll call it C1 is equal to, on the right-hand side, I get x to the fourth over 4 minus x cubed plus 2x squared minus 5x plus another constant C2. So when I took the antiderivative of both sides, I produced two integration constants, but they're both arbitrary. So what you should get in the habit of doing is when you work antiderivatives for equations, just wait until you've taken the antiderivative of both sides and then do one constant C. Don't do a C1 and C2 like this. This constant C, all it is, the way that I've done this problem, all C is it's equal to C2 minus C1.
Will that be applicable in later courses like the C1 and C2, like in next semester or something?
It's just, what I'm showing you is technically what's true. So on this line, technically you produce a constant when you do the antiderivative over here. And technically you produce a constant when you do the antiderivative over here. But because both constants are arbitrary, I could just subtract C1 over, call it C2 minus C1. Since C2 and C1 are both arbitrary constants, the difference of two arbitrary constants is arbitrary. So rather than use two constants, I'm just going to use one constant for both. And that's something that we will always do. You never want to have multiple constants if you can lump them together into one. Okay, so now that I'm at this point, I need to figure out what C is. And in order to figure out what C is, I'm going to use the piece of information that I'm given about the derivative. So if I use the fact that the derivative at 0 is -3, then I can come over here to the side and say, okay, the derivative at 0 would be, well, all of this zeroes out. Everywhere there's an x, it's 0, and you're left with just C. So the derivative at 0 is C, which is -3. So I know that this C that I have here, I know that this is -3. So now I'm going to take the antiderivative of both sides. Again, I've got the antiderivative of f prime equals the antiderivative of all of this. And I fully acknowledge that if you feel like you're pretty good at this and you understand really what's going on, you don't have to put all these steps in. But I'm trying to talk through the idea behind all of this so that once we get to Cal 2, it's a little bit better for you. But yeah, I fully acknowledge you don't need to show all these steps. Over here on the left-hand side, the antiderivative of f prime is just f. Once again, I would produce a constant there. I'm going to ignore that and just do one constant at the end. X to the fourth over 4, its antiderivative would be x to the fifth divided by 5, but there's already a 4 there, so that'll be 20, minus x to the fourth over 4, plus x cubed over 3, but it would be 2/3, minus 5x squared over 2, minus 3x. I've run out of room. Plus another constant. Now, you can call this plus C if you like. I tend to not do that when I work problems because I don't want to confuse it with the C that we had here. So I would say something like, plus K. I use K a lot for constants. So you've got another constant of integration that shows up here. So to do that, I'm going to use the other piece of information I'm given, that f of 0 is 1. I'm going to come down here, go off to the side and say, okay, f at 0 is just going to be K, which is 1. So my answer is x to the 5th over 20 minus x to the 4th over 4 plus 2/3 x cubed minus 5/2 x squared minus 3x plus 1. So you see why we like giving initial conditions at 0. The reason that a lot of initial conditions in mathematics are at 0 is because you don't have to do any work to determine what the constants of integration are. So anytime you're doing modeling, you really want to opt for conditions at 0 if you can. We call those conditions at rest for a model. You really want to know what happens at time 0 or at position 0, because it makes the C and the K easy to calculate. All right, I want to take a look now at there are 2 word problems that I want to get into with you. And these are just straight applications of antiderivatives that we've been working on so far. The first one here, let me just put it up so we can read through it together. We're going to calculate braking distance. So suppose a car is traveling at 25 meters per second. That car begins to decelerate at a constant rate of 4 meters per second squared. After how many seconds does the car come to a stop? And how far will the car have traveled before stopping? So this is what we're going to use to calculate the braking distance for a car traveling at a certain speed. And what I want you to understand is, for this problem, it's no different than the 2 problems we started class with today. It's just in a different context. Mathematically, this is exactly the same as what we started class with. So let me explain. You're told that the car is traveling 25 meters per second. So that is its initial velocity. So let's think about everything that we're given here. The initial velocity of the car is 25 meters per second. The acceleration of the car is, and it's actually deceleration, is 4 meters per second squared. That's the rate at which it decelerates as it puts on its brakes. Okay.
Couldn't you also say that the acceleration is just -4 meters per second?
Yes, and that's what we're going to do. Yeah.
Okay.
We're going to end up doing that here in just a second. Now, I know a lot of you have physics backgrounds, and there are any number of formulas that could help us solve this problem from physics. Every single one of those formulas that you learn in a general physics class, or even in an EP1 class, Engineering Physics 1, they all come from antiderivatives. They're all using the following relationship. We've talked about position functions this semester. We've talked about velocity. We've talked about acceleration. If you go in this direction, you're taking the derivative, right? So the derivative with respect to time of position is velocity. The derivative with respect to time of velocity is acceleration. But if you go in the backwards direction, you're just taking an antiderivative. So the antiderivative of acceleration is velocity. The antiderivative of velocity is position. That's all we're doing. So there's no formulas to memorize. There's only an understanding of how to do antiderivatives. And you'll never have to memorize these mechanics formulas from physics ever again. So I claim that this problem is identical to the problem we just got through working, where we had a second derivative and 2 pieces of information. So let me explain. You're told that the constant deceleration is 4 meters per second. So to put that in math terms, that means that your acceleration function, right, which is the second derivative of position, is it not? Because if you have position, you take 2 derivatives, you get acceleration. So the acceleration, which is two derivatives of position, is equal to -4. As O'Brien pointed out, since it's deceleration, a constant deceleration, then acceleration is -4. So you have a second derivative. Second derivative is equal to -4. And since I'm going to try to recover the distance that the car traveled during braking, distance is about position, I'm going to have to go all the way back to S from S double prime. So if I'm going to have to go all the way back to S, I'm going to have to go back twice, which means I'm going to need two pieces of information. I'm going to need information about the velocity, and I'm going to need information about the position. And I'm going to need, if I want this to be nice, I need information initially for each of these. So I need initial velocity information, and I need initial position information. So let's suppose, that the car is traveling along. This is going to be my attempt at drawing a car. All right. Not bad. So the car is traveling along. We know that its initial velocity is 25. We know that at this time, so we're kind of tracking a timeline here. We know at, I'll call it time equal to 0, the car starts to brake. So we're going to call that at time equal to 0. We're going to call that at time equal to 0, position 0. So at this point, S at 0 is 0. So I'm going to say its position is 0 here. And so that by the time it gets over here, T end, the car has stopped. We're going to want to figure out what the position is at this point, because that's the amount of distance that it took to brake. So that's kind of what the idea is for this problem. And you see that inherently, when I wrote this down, I've given you two pieces of information. We've assumed that the initial position was 0. So that's information about initial position. And we were told the initial velocity was 25. So that's the initial velocity part of this. So what you're being asked to do is solve S double prime of t equal to -4 with V of 0, which is S prime, equal to 25, and S at 0 equal to 0. So this is exactly like the problem we just got through doing. It's a second derivative, and you have two pieces of information to get you back to the original function. So let's do that. If I have my second derivative is -4, I take the antiderivative of both sides. With respect to t here, because t is the independent variable. Then the antiderivative of S double prime is S prime, which is velocity, equal to the antiderivative of -4 is -4t, because I could just pull out the -4, and then I'm taking the antiderivative of dt, which is just t, plus a constant. But here I'm going to be a little bit more deliberate about this. I know this constant, since S prime is velocity, I know this constant is the initial velocity V naught. And so the initial velocity V naught is 25. That's my constant of integration there. So I know that S prime of t is -4t plus 25. Okay, going a step further with it now. If I take another antiderivative, on the left-hand side, the antiderivative of S prime would just be S. So now I'm all the way back to the position function. The antiderivative of -4t is -2t squared plus 25t plus a constant. And this constant will just be the initial position. It'll be S naught. And we know from our assumption that the initial position here is 0. So my position function, S of t, is -2t squared plus 25t plus 0. So that's my position function. Now, we haven't answered the question yet, but we've done a lot of the antiderivative calculus work at this point. The rest is just modeling, right? It's just interpreting what the question is asking us and getting the answer. So the question says, after how many seconds does the car come to a stop? That's this t end distance, right? So after how many seconds does the car come to a stop? And what is the distance the car will have traveled? We call that the braking distance. What's the distance the car will have traveled to come to a complete stop? Okay, so complete stop means what? How would I figure out where I have a complete stop? Anybody?
No velocity.
No velocity, right. So the car stops completely when the velocity, which remember is the derivative of position, when that's 0. So if I go back to right here where I had the velocity formula, that's the derivative of position formula, I need to solve when that function, negative 4t plus 25, was equal to 0. So if I do that the old-fashioned algebra way, you get t is 25 fourths. 25 fourths is 6 1/4. So after 6 1/4 seconds, the car has stopped. So that's what we called t end, the stopping time. Okay, so what is my position 6 1/4 seconds later? That's what we need to find. So what is the position at that point? So -2, 6.25 squared plus 25, 6.25. It turns out the position will be 78.125 meters. So the car has traveled a distance of 78 meters and change and stopped in 6 1/4 seconds. Fit this all on the same page. So there's kind of start to finish what this example looked like. And most of the examples that I could give you are going to look just like this. I mean, there's not much way to make it different other than to maybe give you different initial conditions at different points or something like that. So all of these problems are going to look the same. They're all going to be, you're given some information about a derivative, either the first derivative or second derivative. You're given some pieces of initial conditions. And together you use that with antiderivatives to recover functions that allow you to answer the questions in the problem. And that's the basic idea behind all these applied word problems. You know, and we didn't have to use a single physics formula to do it, which is kind of the point. The formulas come from mathematics, not the other way around. Do y'all have any questions about this example? We'll do one more. And I'll let you kind of dive into the other one to see how far you can get. But are there any questions on this one? All right, so we kind of fall into a trap in math in that, you know, we know acceleration, velocity, and position is important. And so the trap we fall into sometimes is that's the only examples we work. And I don't want to do that because you get so used to working with those that if you run into problems that don't have the same variables, A of t, V of t, S of t, you kind of get a little bit stuck. So this second example has nothing to do with the acceleration, velocity, position, anything like that. But the problem is identical to what we just did, okay? So here in this example, suppose you come in and this is something that actually happens, right? Suppose you come in with, say, like a burn wound or something. And so you're in the hospital, they bandage it, and they usually record the size of the wound because they want to track how quickly it's healing. So suppose it's been T days since the wound was inflicted and first checked, and the area of the wound is decreasing at the following rate. So this is the rate per day that the area of the wound is decreasing. If on the first day after the wound was, I should say inflicted, not inflected. If on the first day after the wound was inflicted, the area of the wound was 2 centimeters squared, what was the area of the wound initially? So we're going to try to go back to figure out how big was the wound initially. And then what is the size of the wound that we would anticipate on day 4 if the wound continues to heal at the same rate? So nothing about acceleration, velocity, or position are here. But I want to see if you can set up the problem. So what I mean by set up the problem is, can you write down the differential equation, just like we had s double prime equal -4 on the last problem? Can you write down the differential equation? And can you tell me what the piece of information or pieces of information are that we need to solve it? So I give you a second to think about that. So don't focus on solving it, just focus on getting it set up. All right, let's see how you did. The way to think about this problem is as follows. I'm going to let the function a of t be the area of the wound after t days. And the piece of information we're given here is what? If a of t is this function, what is the piece of information that you're given here that'll allow us like an initial condition of sorts?
Given a prime of t. So you're given the first derivative?
Okay, so the first derivative, I'll write it as dA dt. So the first derivative dA dt is what?
-3 over t plus 2 squared.
Yep. So that's one piece of information, and this is in centimeters squared per day. That's the rate of recovery. So you're given derivative information, but what I'm asked to find is the area of the wound initially, which would be A at 0, right? So we want to find A at 0, and we want to find A at 4, right? That's the two things we're being asked to find. So find the area of the wound initially, find the area of the wound on day 4. If I'm going to go backwards, which I have to here, right? So I have to get from the derivative of A back to the function A, which means I'm going to have to take an antiderivative here. But if I'm going to go back, I'm going to produce an integration constant. What other piece of information are you given that's going to allow me to solve for that integration constant?
On the first day, the wound was 2 centimeters squared.
Okay, so tell me how to write that mathematically.
You would set it up as the area originally.
Right, but it would be A at what value of t, right? So I'm going to write A of something equals something. What should go there?
A of 0 equals 2 centimeters squared.
I don't think it's 0, right? Because we're trying to find A of 0. The first day after the wound was infected.
A of 1 or
yeah. So A of 1 is equal to 2 centimeters squared. So this is the information you're given. Together, this is the differential equation that we're trying to solve for this model. So let's do that. If I have dA dt equal -3 over t plus 2 squared, take the antiderivative of both sides. And I'm going to write the t plus 2 squared as t plus 2 to the negative 2 on that side. Since it's in the denominator, it carries a negative exponent. All right, on the left-hand side, dt's cancel. We've got the antiderivative of dA. And over here, I'll pull out the negative 3, let's say, so that I'm just focused on this power function. Okay, we know that the antiderivative of the differential is just the function. Now, here's where this is maybe a little bit trickier. Antiderivative, this was in the formulas from yesterday. One of the formulas from yesterday was at plus b to the n dt, or is probably dx, but here we're doing it with respect to t, is at plus b to the n plus 1 divided by n plus 1 plus a constant. But normally, if you were taking derivative of something like this, you'd have to multiply by the inner derivative, which is a. So if the derivative will have you multiply by a, the antiderivative would have to ask you to divide by a. So this is the formula that was in the table for things like this, and it applies here. Basically, the idea is when you see this, you just think of this as something to the negative 2. So the antiderivative of something to the negative 2 is something to the negative 2 plus 1 over negative 2 plus 1 plus a constant. And then you ask yourself, okay, if I was doing the derivative, would I have had to multiply by anything because of chain rule? So the inner function is t plus 2. The derivative of that is 1, which means if I was to do chain rule, I would have multiplied by 1. So if I want to undo that, I would divide by 1, but it doesn't matter because it's 1. So this is the antiderivative of this function. So this is negative 3. Negative 2 plus 1 is negative 1. So negative 3 divided by negative 1 is positive 3 over t plus 2 to the negative 1 plus c. So my function is 3 over t plus 2 plus c. And the information that we're given is that a at 1 is 2. So if I plug in t equal to 1, that should be equal to 2. So I know that this is 3 over 3 is 1 plus c is 2. So c is 1. So my wound model is 3 over t plus 2 plus 1. That's the model. So in particular at A0, that would be 3 halves plus 1, which is 2.5. So initially the wound was 2.5 centimeters squared in area. And after 4 days, we would expect it to be 3 over 4 plus 2 is 6 plus 1, which is 1.5. So after 4 days, we would expect it to be 1.5 centimeters squared in area. So, you know, the thing I keep kind of harping on as we're doing these examples together is that mathematically, all these examples are the same, even though they're in wildly different contexts. The first problem we looked at was just finding a curve that passes through a certain point. The second one we looked at was finding a function that had a second derivative given by a certain value, so we know its concavity at every point. The third example was acceleration, velocity, position, and using antiderivatives to calculate braking distance. The fourth was tracking the area of a wound over time given the rate at which the wound heals. Vastly different contexts, but the mathematics here is the same in every single problem. And so it all just comes down to your ability to take an antiderivative. Antiderivatives are going to be the backbone of Calculus 2. And so I wanted to make sure at the end of Cal 1, we at least talked about them and got those out in front of you so that you'd be able to better understand as we hit the ground running at the beginning of Cal 2. All right, that's all I have for today. That's all I have for the semester. Y'all are free from me for a while. We have an exam on Monday, and then the Friday of the week after Thanksgiving, we'll have a final exam review. But other than that, you're working on your projects and preparing for the final. I'll see you in class on Monday for the exam, or if you're taking online because you are quarantined, we'll figure out what to do for that. So
So the week after Thanksgiving, what day are we gonna come in?
the only Zoom meeting we have the week after Thanksgiving is on Friday.
Okay, thank you.
And that's just to prepare for the final exam. I wanted to give y'all Monday and Wednesday off to work on projects.
And then the next Friday we'll take the exam, right?
I believe y'all's is the next Friday, yes. So I think it's like December 11th. Y'all have a good one.
Quick question. Just like originally looking at the problem, I thought about like taking the derivative and it being arctangent.
This isn't the arctangent function. Arctangent's different.
I gotcha.
Arctangent, so the antiderivative of 1 over 1 plus t squared,
Mhm.
that is arctangent.
Okay,
And you can see that's not the same.
just making sure.
Yeah.
Thank you so much.
Yeah, no problem, O'Brien.
Have a great day, sir. Wait, before I go, actually. I know we're not usually supposed to ask questions about the skill quiz, but when you have pi raised to the power of pi, how are we supposed to treat that as a derivative?
Well, that's a constant.
Okay. Oh,
So that's because there's no x there, right? So
right.
it's a constant, so it's the same as 4, right? So what would be the antiderivative of 4?
Wouldn't it just be the number squared or?
No. So like if you have a constant, right? The constant dt,
Right.
remember you can pull constants out, right?
Right.
So the antiderivative of dt is just t, so you get the constant times the variable. So,
Okay.
so in your example of pi to the pi, right, this would just be pi to the pi times x.
Okay.
Yeah. The antiderivative of a constant is the constant times the variable.
Constant times the variable. So in this case, even though it's pi being raised to pi, you multiply by x?
Yeah, because the variable of integration in that problem is x.
Mm-hmm.
And pi to the pi is just constant. There is no x there.
Okay. Just making sure.
Yep.
Thank you so much.
Yeah, have a good one.
You too.